Hello everyone, welcome to Gradeup. My name is Shantanu Sanwal and here we are for the BYJU'S session on deflection, column and struts and thin cylinders. Okay, till last class we have completed all the topics of the subject of strength of materials. So this is the very last lecture on the previous year solved questions. Okay, so first of all, about the free online GATE ME course, which is designed by GATE toppers and experienced faculties, has a study plan of 90 days. It contains 200 plus video lectures, 250 plus quizzes from all the topics, and also we are conducting the live doubt sessions in a regular interval for clearing your doubts about the subjects that you are being taught at the course. Okay, so the link for that free video course is available in the description box. You can go to that link, click on that link, get subscribed to the course and enroll yourself and start preparing for GATE 2019 examination. So let us see question number 1 asked in GATE 2015 set 1. It says, consider a steel column, having the Young's modulus E as 200 gigapascal, hinged on both ends. Height is 1 meter. Cross section is 10 mm into 20 mm. That means it's a rectangular column. The lowest Euler critical buckling load in Newton is, first of all, write the available values, the available data that we have. E is equal to 200 gigapascal, which can be written as 200 into 10 to the power 3 megapascal. Height or the length of the column is 1 meter. Take it in mm, that is 1000 mm. Cross section, that is the area of cross section, is like this: 10 into 20 mm is square. So we have to find out the lowest Euler critical buckling load, and it is the case of hinged on both ends. Hinged on both ends, that means alpha, the value of alpha is equal to 1. We have the formula for the Euler critical buckling load given by PE equal to pi square EI minimum upon LE square, where this LE is nothing but alpha into L, and in this case the alpha is equal to 1, so LE, the effective length, will be equal to L only. So just substitute the values. PE equal to pi square, E is given as 200 into 10 to the power 3 into I minimum upon L square. L is to be taken in mm, so 1000 square. But now what about I minimum? Where to find this I minimum from? See, there will be 2I in this because the area of cross section is given as 10 into 20. So the 1 will be this, that is 10 into 200 square, 200 cube, sorry, and I2 will be equal to 1 by 12 into 20 into 10 cube. So out of these two, I1 and I2, the minimum one will be, this one will be I minimum. So substitute, just find out this value, substitute it here and get the value of P. So the value of P you will get is 3289.868 Newton. So this is the value that you are going to get, that is 3289.868, that is 868 newtons. This is the value that you are going to get for this thing. So next is,
subscribe to our channel and press the bell icon to never miss any update from Gradeup.
This is the next question. This says a cantilever beam with flexural rigidity, this. So what do you mean by flexural rigidity? Flexural rigidity is the product of E into I, is loaded as shown in the figure. The deflection in mm at the tip of the beam is. It is asking the deflection at this point. Suppose this is A, this is point, the loaded point is B, loaded point is C. So it is asking the deflection, that is Y at C equal to what for this case. So we have yesterday, means in the last class where we were studying about the deflections, where we have studied one thing, that in such cases the deflections at the end is equal to the deflections at the loaded point plus the slope at the loaded point into the distance B into C. So this is only what we have to find out. Okay, so first of all we will find out YB. So if you consider the AB section of the beam, only if you consider that the beam is AB length, so that becomes, so this kind of force becomes a point load and the beam becomes a cantilever beam. AB behaves as a cantilever beam. Okay, cantilever beam. So in that case, cantilever beam subjected to point load at the free end, the deflection is given by WL cube upon 3EI. Okay, where this W is equal to 500 Newton, this L is equal to 50 mm, and EI, the product has been given to you as 200 Newton meter square. But there you have to convert into Newton mm square, because all these values we are taking at Newton and mm. This is 500 into 50 cube divided by 3 into 200 into 10 to the power 6. Okay, so this value you will get as YB, you will get the value as 0.1042 mm. Okay, so this you have find out. Now you have to find out this value, theta B. Theta B is equal to, in this case, the cantilever beam subjected to point load at the free end. The deflection is given by WL square by 2EI. Again, substituting these values, you will get this value as 3.125 into 10 to the power minus 3 radians. Okay, then supplying the values here, so you get YC equal to YB is 0.1042 plus 3.125 into 10 to the power minus 3 and multiplied by the distance, that is YBC. BC distance is 100 minus 50, which is equal to 50. So on solving this, you will get the answer Y at C is equal to 0.26045 mm. Okay, so you can write it as 0.26 or 0.2604, anything you can write, 0.26045. This is the exact answer what we are getting. Okay, simple question, just using this concept we get this answer. Okay, let us see next question. GATE 2015 set 2. This is the question from the topic of thin pressure vessels. A gas is stored in a cylindrical tank of inner radius 7 meters and wall thickness of 50 mm. The gauge pressure of the gas is 2 megapascal. So it is asking the maximum shear stress. Please note down that it is asking the maximum shear stress. Okay, or you can say that this is also absolute tau max. It is asking absolute tau max. Okay, so for finding out absolute tau max, what you will do? First of all, you have to find out sigma 1, that is equal to nothing but sigma hoop. So sigma hoop is equal to PD by 2T. Okay, so P in this case is 2, this one. Okay, so D, that is the inner radius, is given as 7 meters. So inner diameter will be equal to 14,000 mm divided by 2 into this T value is, the thickness is 50 mm. Okay, so if you will cancel out this, you will get this value as 280 megapascal. Okay, then sigma 2, that is sigma longitudinal, is nothing but PD by 4T. Substituting the values, you will get it as 140 megapascal. Then it is asking you the absolute tau max. So the absolute tau max in this case, I have told you, is sigma 1 by 2, because absolute tau max is nothing but the larger, if I tell you in details, it is larger of the whole 3D case. If I tell you, is this sigma 1 minus sigma 2 by 2, sigma 2 minus sigma 3 by 2, and sigma 3 minus sigma 1 by 2. Okay, so in this case it is a biaxial case, so sigma 3 goes out cancelled, so it becomes the larger of sigma 1 minus sigma 2 by 2, or sigma 2 by 2, or sigma 1 by 2. Okay, so just substitute the values. Sigma 1 is 280, 280 minus 140, 140 divided by 2 is 70, comma sigma 2 by 2 is again 70, and sigma 1 by 2, that is 280 by 2 is 140. So the larger of these is this value. So this is nothing but the absolute tau max, or the maximum shear stress that is being asked. So the correct answer, the correct option is option C. Okay, very simple question. Just do not think that it is asking the maximum stress. This is the maximum principal stress in that is 280. This is the minimum principal stress or the minor principal stress, versus 140. But it is asking you the absolute tau max. So absolute tau max, because it is asking maximum shear stress. So maximum shear stress is sigma 1 by 2. Simply we have got this term only. Okay, if you could remember this, it is okay. If you do not remember, just go by the basic definition of absolute tau max and then calculate. You will get the same answer. Okay, so let us see next question. 2016 set 1. A cantilever beam having a square cross section of side A is subjected to an end load. Means it is this kind of configuration. This is a cantilever beam having load W, the length L, and the cross section of the beam, if you see from this side, it is a square cross section. Okay, if A is increased by 19%, the tip deflection decreases approximately by how much percent? That is the question. So for a cantilever beam subjected to a point load at the free end, the deflection at the end is given by, you know, simple WL cube by 3EI. Okay, so now you might be understanding that when I was teaching the topic of deflection or the slope and deflection, I was constantly telling you that you please remember these expressions, these simple expressions for cantilever beams, simply supported beams under point load, UDL, UVL, that I was constantly telling you to remember. Why? Because now you can see that the questions are coming directly on these things. Okay, and you have to directly just remember these expressions, and then you can do the questions very fast. Okay, so WL cube by 3EI is the expression for this. Then you see, if the area of cross section A is increasing, then this will not change, this length of the beam will not change, this 3 is constant, E will not change, only I will change. Okay, I in the case of a square is 1 by 12 A to the power 4, and so Y1, if we take the Y initial, let us write it this way, Y initial in the first case is WL cube by 3EI1. Okay, and Y, or you can write it as initial only, initial. Okay, and Y final means after the A has increased, that will be WL cube by 3EI final. Okay, so Y final, that is after the A has increased by 19%. Okay, so that will be, so first of all you do one thing, find out the ratio of Y final by Y initial, that is the ratio of deflection after the A has increased and initially. So that will be, what you will get that as, that is the inverse relation. So that will become I final upon I initial, that was the I final upon I initial, and I is equal to A to the power 4. So that is directly proportional to A. So final A will be 1.19. Sorry, this was inverse relation I was talking about. This was final, this was initial upon final. Okay, because these are inversely related. Y and I are inversely related. So final by initial, initial by final. Okay, so initial by final, initial I is directly proportional to A to the power 4. So this is A to the power 4 upon 1.19 A to the power 4. So this value, if you calculate, you will get this value as equal to 1 divided by 2 point something, or which is approximately 0.5 only. So you get that the final deflection is equal to 0.5 times the initial deflection. That means the deflection has decreased by, deflection has decreased by how much? By 50%. So the approximately, the deflection decreases approximately by 50%. So D is the correct answer. Okay, very simple question, just that's why I was telling you to remember these expressions. Okay, next is Question asked in 2016 set 2, a thin cylindrical pressure vessel with closed ends is subjected to internal pressure. Okay, this is the condition. Then the ratio of circumferential or hoop stress to longitudinal stress is. Simply, this is very simple question. The hoop stress is given by PD by 2T and the longitudinal stress is given by PD by 4T. So the ratio, that is, it is asking about sigma hoop upon sigma longitudinal is nothing but PD by 2T divided by PD by 4T. You get this as 4 by 2 or the 2. So the correct option is option D. Very simple question. If you remember these expressions, then you do not have to even touch the pen for answering this question. Okay. Then next one. 2016 set 3. A beam of length L is carrying a uniformly distributed load W having the intensity W per unit length. This one. Okay, this is the UDL. The flexural rigidity of the beam is EI. Then it is asking the reaction at the simple support at this one at the right end is. Okay, C. If we take, this is the UDL. Okay, if we take this reaction as R, which we have to find out. This R is only what we have to find out. Now you see one thing. Because of this load at this support, this beam will not go down. Okay, if you write this as point A and this as point B, so the deflection at B will be equal to 0. The total deflection at B will be equal to 0. And the point will tend to deflect downward by the UDL and upward by this reaction. Okay, so the deflection, so that means the total deflection must be 0 or the downward deflection must be equal to the upward deflection. So downward, write down like this, downward deflection due to UDL must be equal to the upward deflection due to point load. This point load R. Okay, point load R, because this R will behave as a point load for this case. So the downward deflection due to UDL, the cantilever beam subjected to point load at the free end, the deflection is given by WL to the power 4 upon 8 EI, and for the point load it is given by R, this is R L cube upon 3 EI. So just cancelling out the terms, EI gets cancelled, this length is same, so this 3 goes with this one, only one left, so R becomes 3 WL by 8. So this is the very simple question which you have to get. So this way you can get the answers for these questions. Okay, very simple question, just using the concept of deflection. Just write this and you will get the answer this way, just equating the deflections, because at that point B point there will be no deflection, effective deflection will not be there. So the deflection which will be caused or which will tend to be caused by the UDL, that will be counterbalanced by the reaction. So this is the way to find out the reaction in this case. Next question, 2018 set 2. The minimum axial compressive load P required to initiate buckling for a pinned slender column. Pinned means both ends hinged. Slender column means it's a long column with bending stiffness EI and length L is. Simply the formula you know, that is equal to pi square EI minimum upon LE square. And since this is a pinned, that means both ends hinged. So LE is generally equal to this. For this case, this alpha will become equal to 1 because it's a case of both ends hinged. Okay, so you will get PE is equal to pi square EI minimum upon L square. Just match the options. Pi square EI by, or EI is okay. EI, if EI minimum is not there, so that is I can also be taken. So this can be written as pi square EI by L square. Pi square EI by L square. So this is the correct answer. Okay. So these are some of the questions that we have to discuss. If you have any queries, any doubts, you can write on the comment box below. And also like the video if you are really liking the work we are doing for you. Share it with your friends and colleagues, and also subscribe to the channel. So till then, thank you, take care, bye.